Hello class, this is CSE 5720, Section 2, Week 4, Fall 2025. Alright, so last chapter we talked about we had our discussion on ER diagrams, which is used to help design a database. Once we have that information in our ER diagram, we can convert that into a set of relation schemas, which then we can use to create our tables in our database. And we're going to do that using SQL. So there are various database languages out there, but the one that you'll probably hear or encounter the most is going to be some implementation of SQL. SQL pronounced SQL. We can make queries with this, but we can also define the structure of data, we can modify data. SQL has various features in it that we're going to talk about. This isn't a complete guide to SQL, but then again, we get to play a little bit with SQL in the labs. You have a lab already assigned to you, and that is Lab 1. You are given a sample database, and you are to do a few basic queries with it. Later on, I'd like for you to try your hand at more complex queries as well. So, as a refresher, it was Edgar Codd who basically wrote the book, or rather, wrote the seminal paper from which we have our concept of relational databases. So everything that we're ever going to talk about for SQL came from IBM System R, also led by Codd. This was where the relational database model was first put into practice. And since then, SQL has become the standard for managing relational databases. So much so that ANSI and ISO have standards for SQL. SQL 86 and its various additions made to it since then. There are various parts to SQL. First is the data definition language. This is what we use to create our tables. Delete tables and make changes to them. That doesn't mean add data to a table. That's for the data manipulation language. That is for making queries and adding, modifying, and deleting rows to our tables. The textbook calls tables relations and rows tuples. I will more or less flip-flop between the two terms, but when I say relation, I mean table. When I say tuple, I mean row. And when I say attribute, I more or less mean column, unless I'm specifically talking about a specific value in a cell. So we have the data definition language and the data manipulation language. There's also commands for specifying integrity constraints. If you make an update to a database that violates an integrity constraint, then that update is simply not done. There's also view definition. In a database, there's going to be some data that not everyone should be allowed to see. So we define different views that block out, if you want to put it that way, it blocks out or only allows certain users to view the information that they are allowed to see. So someone in payroll has no reason to look at stuff in someone in payroll doesn't have any reason to look at a student's transcripts. Someone who's working in the registrar's office likewise has no reason to look at instructors' salaries. We define different views to basically more or less filter what information those kinds of workers are allowed to look at. Transaction control. So a transaction is a unit of work, and it represents a unit of work in which all of it must be done, and in case we can't do any of it because there's an error or we violate a constraint, then none of it is done. So this ties back to our concept of atomicity, where if you have some lump of work and you need all of it to be done, you do all of it, or if you can't, you do none of it. Embedding in dynamic SQL, that has more to do with embedded SQL statements in other programming languages. And authorization, that's also part of the DDL. These are commands for specifying access rights to views and relations. And every SQL database is going to be a little bit different from each other, so in practice, you would consult your user's manual to see what it supports. The data definition language of SQL allows us to specify relations as well as information about each relation, shown here. The schema for each relation, the types of values associated with each attribute, the integrity constraints, so on and so forth. SQL also supports different data types. Most of these are going to be familiar. Most of these are going to be familiar with the data types you've seen in other programming languages. We have char and varchar that are used to represent strings. Char represents a fixed length string of length n. Varchar is a variable length string of maximum length n. We also have our integer data types and floating point data types. There's also a numeric data type, which is p digits to the left of the decimal point and d digits to the right of the decimal point. So this is a fixed point number format, as opposed to the floating point formats we see with, say, float and double. There are more types discussed in section 4.5, but there's also the null value that we've talked about several times already. Both char and varchar are used to store strings, but since char is a fixed length string, if you enter a string that's less than n characters long, it's going to have spaces appended to it. This might mess up with string length comparison operations, so it's recommended to use varchar over char. There's also nvarchar, which is a variant of varchar that supports Unicode, but some implementations allow Unicode to be represented in a database in UTF-8 representation. So once we have those ER diagrams, we can turn them into a set of relation schemas, and that is enough information for us to create a table in a database. So for example, create table department. So department is a table of departments in our ongoing university example that we're going to keep seeing throughout the book. It has 3 attributes: department name, building, and budget. So 2 of those data types are varchar because, well, we need to represent them textually, and budget is a numeric data type that we use to represent how much money is this department allocated. We also get to specify the primary key. It's highly recommended that you specify a primary key. In this case, the primary key is department name because in our ongoing university example, we want to be able to uniquely identify every tuple in a relation, and that's what the primary key is for. It is a set of 1 or more attributes that we can use to uniquely identify each row in a table. Since every department is going to have its own name, we can declare department name to be the primary key. Here's a general form of that create table command. We can specify integrity constraints such as the primary key, but we can also specify a foreign key and a not null constraint. The primary key constraint specifies a set of attributes to be used as the primary key. Here are the requirements. Attributes must be non-null and unique. The foreign key specifies a set of attributes in a relation that are found in another relation. The attributes listed must be present in the referenced relation. And of course, not null. This is not a constraint that goes into one of these lines. Rather, it's added on to the lines that specify an attribute and its data type. So we can say attribute name, data type, and then add the words not null after that to say this attribute cannot have null values. Updates that violate integrity constraints are disallowed. If you make such a change, it's not made. A simple example would be a null value being entered for a non-null attribute. A more complex example would be demonstrated using the foreign key. So, this is an example of what is called referential integrity. If we have a table of courses, our primary key is going to be the course ID. If we add a table of courses, we can only add courses if the department that it's referencing exists. So we can only add a new art class, say Art 404, if we already have an art department. We cannot add a class called Ethics of Time Travel because there's no time travel department in our university. We can add an instructor, but we can only add one if we are adding an instructor to a department that exists. We can add someone to teach in the art department, but we can't add someone to teach in the time travel department because that department doesn't exist. Similarly, we can only add sections to courses if those courses already exist. So, section, as we've seen in Chapter 7, requires 4 primary key attributes. The first one is going to be the course ID, which is going to be referencing the course relation, but it also requires the section ID, semester, and year. We need all that information to uniquely identify every course in our university. So, for example, if you have a section 1 of microtonal music theory and a section 1 of 3D modeling, if we did not have the course ID, we could not tell them apart. That's basically what I'm saying. So we need that extra attribute, course ID, to tell each one apart. There's also the section ID, semester, and year. So those 2 classes I talked about, microtonal music theory and 3D modeling, they could have the same section ID of 1. So section 1 of their respective courses. They could be taught in the same semester, in the same year. And that would not be enough to identify each one until we add the course ID. Additionally, we cannot add a section for a class called Ethics of Time Travel because there's no course for Ethics of Time Travel. And of course, we can't add that because there's no department in our university that is the time travel department. Finally, we can only add teaching assignments. So instructors are assigned classes to teach, or I should rather say courses, or rather sections to teach. We cannot add teaching assignments unless the section exists and the instructor exists. So even if we have an instructor, we cannot add a teaching assignment to an instructor for a class of Ethics of Time Travel because that class doesn't exist. Well, there's no section for Ethics of Time Travel because the course for that doesn't exist, and the course for that doesn't exist because we don't have a time travel department in our university. So all that is to say is we are only allowed to add entries. We're only allowed to add sections for a class if they exist. We can only add courses for a department if that department exists. These are far from the only referential integrity constraints in our database, but this should give you an idea of what it means to have referential integrity. Also, similarly, we can only teach a section in a building that exists. Once we make a relation using the create table command, it's going to be empty. But we can add new data using the insert command. So we can just say insert into instructor values, and then we can just list off each value. So we're adding instructor Smith to the biology department with a salary of $60,000. Delete from removes a relation from a database. It deletes the tuples, but it preserves the schema. So it basically empties out the table. Drop table, however, removes the relation in addition to removing everything stored in the table. So not only have you removed everything from the table, you've also removed the table itself. Alter table lets us add new attributes to an existing relation. When we add a new attribute to a table, and there's already data in the table, existing tuples will be assigned null values for the new attributes. So alter table, table name, add attribute, data type. And then any existing rows just get null values for that new column. Alter table can also remove attributes from a relation. Oh, and speaking of drop table, this is going to become more important when we start talking about security in a database. By the way, as I mentioned in class, you are really playing the long game if you name your child Robert Drop Table Students. And I hope you've learned to sanitize your database inputs. So, a big part of this chapter is understanding how a query is evaluated, or how to conceptualize how it would be evaluated. So a SQL query consists of three clauses: select, from, and where. So we select one or more attributes from a relation that satisfy a predicate. Here's a simple query. Find the names of all instructors. So that would be select name from instructor. This returns a table that contains all instructors' names. Select name from instructor. Here's another one. Find the department names of all instructors. So this is select department name from instructor. So if you recall from the instructor table that we've seen, if you recall from the instructor table that we've seen a few times already, it had 4 attributes: ID, name, department name, salary. So what we're doing is basically selecting one of the columns from our table and displaying it as its own standalone table. Because the result of a query is another table. Okay, but look at this. We have all the names of all our instructors by saying select name from instructor, but we also have select department name from instructor, and if you look closely, we have duplicates. To next that up, we can add the distinct keyword after select. This is something you're actually going to do in your lab. So to remove duplicates, we add the distinct keyword after select. The opposite of this is adding the all keyword after select. So, select distinct, that removes duplicates. Select all preserves duplicates, but the default behavior of select by itself is to preserve duplicates. So select all is redundant. We can also perform math operations in a query. So we could say, for example, show all instructors from our instructor relation, but apply a 10% raise. This does not change any of the data already in the database. Rather, it just it multiplies the salaries in the resulting table. So we can say select ID, name, department name, and then salary times 1.1. So far, none of those queries involved the where clause. Let's talk about that. The where clause allows us to show results that satisfy an attribute, such as this. This query is show all computer science instructors who make at least $70,000. And the result of that query is 2 instructors. And the query looks like this. Select name from instructor where department name equals computer science and salary is greater than $70,000. Logical connectives and or and not can be part of your where clause predicate. The comparison operators of less than, greater than, their variance where it's or equal, equals, and does not equal, those are all allowed also. So far, our queries were working with one table, but we can make queries that work with multiple tables. So here's another query. Retrieve the names of all instructors, their department, and the building for that department. That is select name, instructor.department name, building from instructor and department, where instructor and department name equals department.department name. The result of that query is a 3-column table where we have the names of all our instructors, the departments that they work at, and the buildings at which those departments are located at. In the case where we have 2 tables with the same attribute name, we have to disambiguate them by saying, in our case, it's instructor.department name, because both department and instructor have an attribute called department name. So by saying instructor.department name, we make it clear about which department name we're referencing. Name and building don't appear in both of the original tables of instructor and department, so we don't have to disambiguate them. So the more general form of a SQL query is as follows. Select one or more attributes from one or more relations where it satisfies a predicate that might contain logical connectives of and or not, less than or equal, greater than or equal, equals, and does not equal. So here's how we can step through the process of how a query is evaluated. Here's how we conceptualize it. So the clauses are written in the order of select from where, but for our purposes, we're gonna treat it in the order of from where select. We're gonna try this simple query here. Select name and course ID from instructor and teaches, where instructor ID equals teaches ID. Let's start at that from clause. So the from clause takes the specified relations and it finds the Cartesian product of those 2 tables rows. So this is also called a Cartesian join. We take one row and then produce a new row where it is combined with every row in the second table. And we do this for every row such that if we have m rows in instructor and n rows in teaches, we get an m times n table, where it's m times n rows, I should say. So the Cartesian product of these 2 tables is going to be, well, first, it's going to be containing all the attributes of the 2 tables, but the final table can't fit on the screen, so I have to show you an abridged version. So this new relation is huge. The original relations had 12 and 15 tuples, so now we have 180 tuples in our table here. So it combined every row from both tables in every possible way. It even combined them in ways that does not make sense. So Srinivasan is a physics instructor, but look, there are instances where the instructor ID does not match the teacher's ID. Also, Srinivasan teaches physics, not music. No, Srinivasan only teaches computer science classes, not physics, not music. So a lot of these rows in this table don't make sense. So what we need to do is eliminate all of these nonsense rows. And that's what the where clause does. It removes the tuples that don't make sense from the Cartesian join. So let's look at our where clause, where instructor ID equals teacher's ID. And we've just seen an example of where the values for ID did not match here and here. So we just remove those rows. And remove every row in which the value for instructor ID and teacher's ID does not match. So now we've eliminated all of those rows, but we're not done with our query just yet. We need to evaluate the select clause last, and that is select name and course ID. So all you gotta do is just select the name and course ID columns and eliminate everything else. There we go. And just like that, we have our final query. So a SQL query can be thought of as performing these three steps. Perform a Cartesian join on the relations specified in the from clause, apply the predicates specified in the where clause on the resulting relation, and then put the attributes specified in the select clause. So this query is for all instructors in the university who have taught some course, find their names and the ID and the course IDs of all courses they have taught. Basically, show all instructors and the classes that they teach. Or more specifically, show all instructors who teach a course and the classes that they teach. You notice those little asterisks I put here? So there is a little bit of a caveat that I need to mention right now. And it is this. In practice, SQL does not make any of these circled rows here. In practice, to find the entire Cartesian product is seldom useful. It takes time to find the whole thing, and as I've mentioned, a lot of these rows are nonsense. So in practice, SQL is optimized to only make the rows that do make sense. In that regard, we can think of the where clause as a filter. Basically, it prevents the system from producing a row where, in this case, the instructor ID does not match the teacher's ID. So all the rows that I've circled here, although we can conceptualize a query as starting off with a Cartesian join and then producing all these rows, in practice, those rows are just never made to begin with. Due to the issues with Cartesian join, SQL also supports natural join. So we're gonna do another query on the same two tables, and it's gonna be as follows. Again, we're gonna do from where select order, where we're gonna select name and course ID from instructor natural join teaches. Watch. So natural join is a little bit different from Cartesian join, where we merge rows based on whether they have matching values for matching attributes. So let's look at the IDs here because both tables have an ID attribute. Let's start with Srinivasan and see that we have 3 rows with the same ID as Srinivasan. We combine this row with these 3 rows, one at a time, to produce these rows in our natural join. So the first 3 rows are for courses taught by Srinivasan, and then Wu, and then Mozart, and so on. Now we have this table, which only has 15 rows in it. The next step is to apply the where clause, but our query did not have a where clause, so let's go to the select clause. The select clause says to select the name and course ID columns in our table here. So we just select those, cross out everything else, and there we go. This query gave us the same result as the other query that used our Cartesian join. In other words, these two queries gave the same result. The only difference is one is shorter. A query can perform natural join on multiple relations. In general, the relations specified in the from clause can be composed of multiple relations. Each relation or join is either one relation or two relations joined together. So we can do relation, natural join, relation, or we can do relation or join, comma, relation or join, comma, relation or join. It means, in other words, we can mix or match Cartesian join and natural join. When you do so, just keep in mind the order in which tuples are concatenated. So here's an example of two queries that might not produce the same results despite using the same relations. So the only difference between these two queries, so we are joining three different tables together, and the difference is how we join them together. One is natural join and then Cartesian join, if you evaluate this from left to right, and the other one is natural join followed by another natural join. So let's walk through that step by step. It's going to be a little bit tricky because my webcam is going to be covering up some of the tables, but I'm going to do my best to make sure my face isn't in the way. So let's start by evaluating the first query. Let's start with the from clause of from instructor natural join teaches, comma, course. That means we're going to do a natural join on instructor and teaches. And like before, we're just going to merge the rows from one table with the rows of the other table for which the ID values match. And then we get this table, the natural join of instructor with teaches. And then we Cartesian join this with course. So they're all combined in every possible way. And again, this would not fit in the slides, so I'm only gonna show you what it looks like to combine everything with the first row and everything with the last row. So now we have this big table. The next step is to apply the where and select clauses. Tuples where the course ID attributes do not match are removed. Where teachers.courseID equals course.courseID, we just cross everything out where the two course IDs don't match. We're going to stop here because we're more interested in how the relations are joined. So let's try the second query, where that one was natural join followed by another natural join. So the first natural join is performed the same way as before, but now we're going to need to natural join this with this. But there are now two attributes whose values must match, department name and course ID. Because natural join concatenates tuples based on whether their respective values for matching attributes match. But because there are two attributes in common, the values for both attributes must match. So, for these two highlighted rows, Suni Vasan teaches a computer science class, that is CS101. Does it match this information here? CS101 computer science? Yes, they do. And then we repeat this process for all other rows. If you're to conceptualize this as code, it's basically a nested for loop. So for each row in this table, we're going to combine it with each row in this table. The result is this table where we have ID, name, department name, salary, course ID, section, semester, year, title, and credits. And it looks like we're about to produce the same table as we did in the previous query, where it was natural join, then Cartesian join. This is natural join, and then natural join again. The last step would be to select the name and title columns in this table. However, there is a slight difference between this query and the previous query. If an instructor teaches a section in a department different from their own, that tuple will not be included in the final relation. To demonstrate what I mean, let's consider a simple example where Brant, in addition to teaching computer science, teaches an Art 404 class called Intro to 3D Modeling. So let's try our query on this simple instance of the dataset where we just have one row in each of the three tables. Let's try it out. So we have instructor, teaches, and course. We're going to do the same query where it's natural join, then natural join. Watch what happens. So the first step is to natural join instructor and teaches, and then we natural join the result of that with course. But the thing is this: both the values for department name and course ID must match. The course IDs matches, but not those for department name. Therefore, when we natural join instructor, teaches, and course, we get an empty table. So this is to show that Cartesian join is generally too inclusive and natural join is sometimes too exclusive. But there's even a way to fix that. We can specify which attributes to join. So let's modify our from clause and add using course ID. If we add that, it basically says, no, only match along the course ID. And when we do that, even though department name does not match between these two rows, well, it doesn't matter because we're not considering that. What we're only considering is only the course ID. And only the values for course ID need to match. And because of that, our table's no longer empty. So let us reevaluate our sequence of steps. So evaluate the from clause to get a relation. If present, apply the predicate specified in the where clause on the resulting relation. And then output the attributes specified in the select clause. And if you are performing a Cartesian join, only produce tuples that satisfy the where clause. That took a while, didn't it? Right. Take a breather, and let's look at even more operations. Let's look at this query and its result. So select name, course ID from instructor teaches, where instructor ID equals teacher's ID. Here's the two relations. So here's the two relations, and here's the result of that query. For all instructors in the university who taught some course, find their names and the course IDs of all courses they've taught. Basically, find all instructors who have taught a course, display their names, and the courses they've taught. So, as I said, the result of a query is another table. And the attribute names for this resulting table is actually derived from the tables referenced in our query. So name came from the name attribute in the original table, same with course ID. Sometimes you cannot derive an attribute name in this way. For example, two relations might have the same attribute names, so the result could have duplicate names. If your select clause includes an arithmetic expression, then the resulting attribute will have no name. And sometimes you just want to change the name. So the as clause, AS, the as clause lets us rename attributes from a relation, or we can rename the relation itself. This does not affect the original relation or its attributes. It's an alias. So original name as alias, if we say instead select name as instructor name, and leave the rest of the query the same. The only difference is that we renamed name to instructor name. And again, this is only for the output table, because the output of a query is a relation, another table. The as clause is also useful for shortening long names. So, instructor as t, teaches as s, where t.id equals s.id. We can also use the as clause to compare tuples from the same relation. So we can have a query that looks like this: instructor as t, instructor as s. This query says, find all instructors who make more than at least one biology instructor. String operations. So your first lab does not have any questions regarding string operations, but I think it's a good idea to talk about what operations you have. Strings in SQL are enclosed in single quotes, so it's kind of like Python. Although Python lets you do strings enclosed in single quotes or double quotes, in C++ it's double quotes only. If it's single quotes, that means it's a string. It means it's a character, not a string. Strings are case sensitive. Some implementations are not case sensitive, however. String concatenation is done using two pipes. Converting to uppercase and lowercase is done using the upper function and lower function. Removing extra spaces is done using trim that removes extra spaces at the end. You also have other operations for extracting substrings from a string and finding the lengths of a string. What operations are available to you may differ between systems. Pattern matching is done using the like operator, and there are two special operations for this: percent and underscore. Percent matches substrings, underscores matches singular characters. They're also called wildcards. Patterns are case sensitive, so intro percent matches any string that starts with intro, such as intro to computer science, or intro to 3D modeling, or intro to microtonal music theory. Percent comp percent matches any string that contains comp as a substring, like intro to computer science and computational biology. 3 underscores matches a string of exactly 3 characters, but 3 underscores and then a percent matches a string of at least 3 characters. Patterns are expressed using the like operator. So this query says, well, it obviously says select department name from department where building like % Watson %. That means find all departments that contain the name Watson in the building name. Pretty simple. If a special character is actually part of the string, and you should not treat it as a special character, we can define an escape character. So if we are looking for the string any % sign, where the % is part of the string, we can define an escape character, such as backslash, before %, and then add escape, and then in single quotes, backslash. So it looks like this. Like any backslash %, escape backslash. And that's how you define an escape character in a query, where % and underscore are part of your string. They're not to be interpreted as a special character. Here's another special character, the asterisk. It's another wildcard that you can use in the select clause to denote all attributes. So you can say select instructor.star. That selects all the attributes in the instructor table. If you use it by itself, it will select every attribute from all the relations you specify in the where clause. So if you say select star, it's going to select all the columns. In practice, this is probably something you don't want to do, just to avoid any issues with readability and duplicate attributes. The order by clause, which is something you're also going to do in your lab, sorts tuples in lexicographic order, usually alphabetical order, or ASCII-betical order. By default, this is done in descending order, or by adding the ASC keyword, the ask keyword. To reverse the direction, add DESC, desk, or des. So, select name from instructor where department name equals physics, order by name. This basically says, show all instructors who work at the physics department, alphabetize their names. Alphabetize them by name. Here's a similar query. Select everything from the instructor table where show everything from the instructor table where department name is physics. Order by salary ascending. No, order by salary descending. Name ascending. There's also a few ways we can simplify where clauses. So if you want to specify something in a range, you would write something such as value, attribute name is less than or equal to minimum value, and attribute name is less than or equal to max. Let me repeat that. Attribute is less than or equal to min, and attribute is greater than or equal to min, and attribute is less than or equal to max. That's a mouthful, and that's why we can use the between keyword to say attribute between min and max. And the opposite of that is not between. So select name from instructor where salary is greater than 90,000 and salary is less than 100,000. That's a mouthful. Just the where clause is a mouthful. Where salary is greater than 90,000 and salary is less than 100,000. That's a mouthful. We can simplify it to where salary between 90,000 and 100,000. We can also simplify comparison operators. So we have something like this, where instructor.id equals teachers.id and department name equals biology. There is an alternate way of writing this, and we write it as a comparison between two tuples. So the where clause can be written as instructor.id equals teachers.id and department name equals biology. This is an alternate way to write the same thing, where instructor ID, department name equals teacher's ID, biology. And this works for any arbitrary tuple of arity n. And that's all I'm going to talk about for Chapter 3. There is a lot more we can talk about in Chapter 3, but I think I'm going to have to save that for next week and then see how you are with the first lab. So the first lab, there is an accompanying video. It's by my brother. There is a set of accompanying slides that tells you what to do. See how far you can get with that, and we'll go from there. After that, I think I want you to do more complex queries that involve one of the two join operations, like Cartesian join and Nettl join. But we'll see where we go. We'll see where we are from here next week, okay? All right. That was a bit of a long-winded discussion, but yeah. We're starting with queries and working our way up to more complex operations. We're only in the basics right now. So, with that, I'll see you next week, and we'll look at more SQL basics next week as well. Okay? All right.